So now we'll go through the B1 reflection solutions. Remember, if you have a question, feel free to share it in that last free response. It's very helpful for me if you tell me that you watched the video, but you still don't understand it. So if I see enough of that going on, I will try to go over a problem in class or the affected problem. So question 1, we have a simulation. So the simulation typically is a little hard for you guys at the beginning, so this is normal. And we have criticized the following simulation. A student simulates the outcome of a basketball player's three-point shot by letting 0 equal a missed shot and 1 equal a made shot. So the problem with this is that means that you are automatically assuming if you have 0 and 1 and they're equally probable, you have a 50-50% chance of making shots. And for three-point shots, this may be unrealistic. Maybe they do better. Maybe they do worse. So the simulation will not model the real situation. The simulation assumes a 50-50%. So if we knew how good the student was, let's say they made a 70% shot, then we could say, oh, 0 to 6 is making the shot, because that would be 7 digits. And then 7, 8, and 9, that's 30% of the digits is missing the shot. So that one would make more sense. I really struggled with writing the plan for simulating 5 devices to test the given numbers. I had to rewatch the videos about the topic multiple times, and I still feel like I've done it all wrong. I struggled with question 3 because I wasn't sure how to write the component trial and response. I understood the process to check if a machine is working, but I'm unsure if there's a specific way to write down the component trial and response. Okay, so first of all, don't get too tied up in this component trial and response. I was trying to structure it for you to make it a little easier for those of you who like structure. So let's go ahead and look at the scenario. We have a complex electronic device that contains 3 parts, A, B, and C. The probabilities for failure for each part in any one year is 0.01 or 1%, 0.03 or 3%, and 0.04 or 4% respectively. So part A has a 1% chance, part B has a 3% chance, and part C has a 4% chance. If any of them fail, then the device won't work. So there are multiple ways to answer this correctly, but I'm going to give you probably the cleanest one, all right? We're going to write up a plan to simulate 5 devices, and we're going to test if they're working using the random numbers on that line. So how many are working based on your plan? So we're going to check each part. That means each digit represents 1 part. I'm sorry, I'm trying to do 1%. So not each digit, but each 2 digits. Now, why is that? Well, for 1%, I need to have 1 outcome out of 100 represent a failure. How many digits do I need to represent 100 outcomes? Believe it or not, for 100 outcomes, you only need 2 digits. Why? Well, you have the digits, the pairs of digits 0, 1 to 99. That's 99 outcomes. But if you include 0, 0, then that basically works as your extra outcome. So you have 100 outcomes. So you can actually mimic 100 outcomes with 0, 0, or with 2 digits, I should say. And you can mimic 1,000 outcomes with 3 digits, even though 1,000 has 4 digits in it. So it's these 100, 1,000, 10,000, where you get to go 1 digit down. You just basically look at the last 3 digits and you know what it is for 1,000, okay? It'll take some practice. I know it's a little hard. So for part A, I need 1 outcome not to be working, and then another 99 to be working. So I'm saying 0, 0 is not working. All right. Now I could flip and say 0, 0 to 98 is working and 99 is not working, and that's fine. But I'm going to stick with this for this example right now. Then for this one, I need 3 out of 100, so I need 3 outcomes. 0, 0, 0, 1, 0, 2. All of those are not working, and the rest of them are working. I need 4 outcomes for component C, because it's 4 out of 100. So it'd be 0, 0, 0, 1, 0, 2, 0, 3 are not working, and then the rest are working. So I test each one. If all 3 are working, then the part is working. And I'm going to do 5 trials, all right? So because I'm testing 5 devices. And the response variable, what I'm recording is the number of devices passing out of 5 devices. So here we go. Here are the first 3 pairs of digits. 95, we said, is working. 63 is also working, and 99 is working. So this one passes. Device 2, we have 97, 54, 31. Since we have no low digit outcomes, that also passes. And then you have 19, 99, and 25, and all those 3 devices passes. And then 58, 68, 36. So since I don't have anything in the 0, 0 or the 0, 0 to 0, 3 on these pairs of digits, all my devices are working, which kind of makes sense because this is a very low probability that they're not working. So let's look at another response. So if we said 0, 0 to 98 is working, then 99 is not working. And then remember how I said you could do it the other way. So I'm kind of flipping it around. And I'm saying the first 99 outcomes is working, the 100th is not. The first 97 outcomes right here is working, and the last 3 are not. The first 96 outcomes are working, and the last 4 are not. So here you can see 95 is fine, 63 is fine, but 99 is not working. So it's work, work, not work. So this one fails. This one's working because I didn't hit 99. And then this one's working, and that one's working. Then for this one, we have working, not working, working. So that one fails. So device 2 is working, device 1 is not. Device 3 fails. Device 4 passes because none of these are very high. Device 5, we have that 98, which falls into the not working for device B. So that one fails. So depending on how you set it up, that can affect what is a pass or a fail for the whole device. So these are a bear to grade. So they're kind of I try to avoid putting myself in this situation too much, but I do have to make sure that you can't do this. So if you decide to do this version instead of that version, I have to understand what you're doing and make sure you're running it correctly. You can write your own instructions as long as the instructions make sense and you follow them, you're in good shape. Okay, question 4. I also struggle with 4, which I didn't think it was in the notes. I originally thought it would be predictable since it was a regular distribution. If the individual outcomes of a phenomenon are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of trials, we say the phenomenon is random. Now, we don't tend to say it's uniform. You could say rolling a die. That's actually a regular distribution of outcomes in a large number of trials if we wanted to say it was uniform. But maybe we don't really define what a regular distribution is. But what we do know is that we can't predict the outcome. And that's the main thing. That's the definition for random. Okay, question 5. A study of marital status of adults in the United States results in the following segmented bar chart. Which of the following is the greatest? Well, the problem here is that we don't know how many people were in every study. You could have had 2,000 people in this study and only 1,000 people in the 1950 study. So anything that says number probably doesn't work. So A doesn't work. Let's see. Now B, the number of adults in 1900, which of the following is the greatest? The number of adults in 1900 who were married, I have no idea because I don't know how many were surveyed. 1/2 the number of adults in 1950 who were married, I don't know. I don't know how many were surveyed. The number of adults in 2000 who were widowed, divorced, or never married, again, have no idea. And I don't know, they all look equal because that's a relative frequency. It goes to 100%. But you could have had 1,000 here, 500 there, and 10,000 there, and you don't know. So you cannot compare individual numbers. So it is impossible to determine the answer without knowing the actual numbers of people involved. On to question 6. I struggled with number 6 because I thought if you're combining the classes, you just needed to add 87 and 98 and then divide by 2, but that wasn't the answer. So let's go ahead and look. This is called a weighted average. So if the average score for the first class is 87 and you have 25 students, that's kind of like you have 25 87s. But you have 30 students in the second class, so there's a little more. And so you have 30, and their average is a 98, so you have 30 98s. You add up all those points together on top, and you divide by the total number of students, and that is what gives you a 93. So we're weighting it by the number of students in each class. So hopefully that makes sense. Question 7, struggling with finding the proportion of 20-year-olds who expect to survive to the age of 60. I added the numbers surviving for age 60 and 80 since that means they live past 60 and divided that all by the number surviving, but got a much lower number. I'm not sure how to find the proportion if that's wrong. I don't understand how to get the answer to number 7. I struggle with number 7. Let's go ahead and do number 7. All right. So, what is the proportion of 20-year-olds expected to survive to the age of 60? So, given that they survive to 20, how many of those survive to 60? Well, if they survive to 60, they definitely survive to 20, so that's fine, right? And how many people survive to 60? That is 7,800 people, all right? Let me go ahead and get my laser pointer. Here we go. So these people survive to 60. And you don't get to 60 if you don't make it to 20. So you have to make it to 20 and 60. And then we're only counting the people that did make it to 20. So that's the 9,700. So you just divide those two numbers, and that gives you 0.8041, or roughly 80.41%. Question 8. A class survey. Here's a small part of the data set that describes the students in an AP Statistics class. The data come from anonymous responses to a questionnaire filled out on the first day of class. So who are the individuals in this data set? Well, the individuals in the data set are basically the people we're surveying or gathering data on. Well, we said the data set describes the students in an AP Stats class. So it would be the AP Statistics student. Then the next question for this is, which of the following is not a categorical variable? First of all, gender is male, female, or other. So that's definitely categorical. Those are not quantitative values. Grade level, well, it looks like it's quantitative, but it's really pushing it. You don't normally average grade level. That's a good way to look at it. Children in the family, well, you can average the number of children in the family. That's fine. Now, homework last night in minutes. If I was only looking at the column header, I would be totally tempted to say this is my quantitative data. But they've sort of turned it into categories. How did they do that? They said, oh, okay, so we have the 0 to 14 minutes. So people were just checking boxes off on which range they fell into. You can see they kind of broke it up into every 15 minutes. So when you do that, that sort of turns it into a category. And then Android or iPhone, that's obviously categorical. So the one that is not categorical is children in the family. On to number 10. The relative frequency of the brands of the last 45 digital single lens reflex SLR cameras sold on a popular internet auction site are displayed here in the bar graph. Which of the following conclusions can we draw from the information provided? Well, it says Canon sells more cameras in the United States than in any other country. I don't think so. Well, I have no idea. We don't have country data. All right. At this internet auction site, Canon seems to be as popular as all the other brands combined. And I think if I stack these together, they would be roughly equal. So it's possible. It seems correct. All right. C, of the most recent sales at this site, approximately 50 Canon, 12 Sony, 25 Nikon, and 10 Fujifilm, and 5 Olympus cameras were sold. I have no idea. These are relative frequencies. I don't know actual frequencies, all right? Absolute frequencies. Women tend to prefer Canon cameras, while men tend to prefer the Nikon. I have no preference by gender, so I have no idea. According to the information provided, Canon is preferred twice as frequently as all the other brands combined. I would say it's probably equally as frequent, not twice. Not twice. So the correct answer was, the correct answer on this one is B. B is the correct answer there. Okay? Now we give you some data. And Joey's first 14 quiz grades in a marking period were as follows. By the way, that's a lot of quiz grades in one marking period. And they ask you for the mean. So what I'm going to recommend is that let's go ahead and go to Stapplet. So I'm going to go ahead and we have one quantitative variable. I'm going to use the Stapplet and it's single group. So we'll go ahead and use this. And I have the data already. I'm just going to paste it in. You can separate it with spaces and or commas. Begin your analysis, and there it is. And you can see there are the summary statistics. The mean is 85, and the median is also 85. Now, so the mean, the answer to question 11 is 85. It's right there. Now, the next question asks, suppose Joey has an unexcused absence for the 15th quiz and he receives a 0. So what I'm going to do is I can edit inputs right here. And let me go put a 0, comma 0. And begin analysis here. And you can see that the new mean is 79.33. So what's going on is this dot is skewing all this data. So the median moved a little. It moved from 85 to 84, but the mean got pulled down all the way to here by that 1. So now that we've used Stapplet, what is the mean of Joey's quiz grade? So I'm bringing in the 5-number summary, and then you can see that the mean is right here. It's 85, and so the answer is D. Then let's say he actually had a 0. So you saw where I added in that data point of 0. What is the new mean of Joey's quiz grades? Well, here's the 5-number summary plus the mean and the standard deviation. The new mean is 79.3. So it's either A, B, or C. It is not resistant to outliers because that 85 went down to 79. It went down almost 6 points. But we don't really say that a mean is skewed. Distributions are skewed, but not means. So what we really say is that the mean is not resistant to outliers. Now let's look at his median. Now if you look at the summary stats, you can see there's the median. It's 85. And then when we add in that 0, my new summary stats, my median becomes 84. So what that means, it's pretty close still. So resistant doesn't mean, oh, I don't know why I have the mean circled. It should be the median. All right. Resistant doesn't mean that it's not going to change at all. It can change a little, but it's not going to change as much. Remember, our mean went from 85 to 79. That was a 6-point swing, whereas this is only an 84-point swing. Experts, so feeling sleepy. Students in a high school stats class responded to a survey designed by their teacher. One of the survey questions was, how much sleep did you get last night? And there's the dot plot. Experts recommend that high school students sleep at least 9 hours per night. What proportion of students in this class got the recommended amount of sleep? So at least 9 hours would be this group right here, which is 5 data points, and I added them all up. I just went and counted 1, 2, 3, 4, 5, 6, etc. And there are 28 total data points, 5 of which got at least 9 hours. So all I do is just divide the 5 by 28, and I get 0.179, and that is the proportion. Finally, question 16, we ask you to describe the shape. I don't know why it's F, G, H, I, J. It should have been A, B, C, D, E, but that's fine. All right. So we're going to count this as roughly symmetric or fairly symmetric. And you might be tempted to say it's bimodal, but honestly, this is still kind of one pile of data. It's pretty, so we're going to say this is fairly symmetric with a single peak at 7. This does not really feel bimodal. And hopefully that answers all your questions on this assignment. Feel free to let me know what you're still wondering about in that last free response question. Remember, the highest point is 7. There's no real gap between 6